Hey, welcome to Automat Live Coding, although today that name may not be the most fitting because we will not be doing a lot of coding today. Normally on this stream we are writing a desktop automation tool called Automat, where you can connect those small toys to perform actions. Here I can create a timer that will count a very short time, like some milliseconds, and it will tick. And you can hear the ticking. You can barely see it because this is a development build and we broke a lot of the rendering, so it's not working that great right now. Yeah. When I remove the cable, it suddenly starts working faster. It is what it is. During the last stream we had serious trouble with compiling this stuff, or not compiling, making it work. And oh, look at that. Turns out it was not a programming issue, it was an issue with compilation flags. It was a nasty one. Anyway, off stream I figured out what it was and fixed it. And I did a lot of cleanups off stream again recently, but this is all irrelevant. This is not what we are going to be doing today. We will come back to this maybe on next stream, or maybe I will finish this offline, because this whole multi-threaded rendering, I know it's not very visually kind of interesting. It's basically about looking at the code for a very long time and doing incremental cleanups and small improvements. Today we will be doing something slightly different. There are a couple projects from the Future of Coding space that we will take a look at. All of them come from the Future of Coding newsletter. So if you know how to sign up for that, yeah, check out this futureofcoding.org and you should find the newsletter somewhere around that page. So this is the first project that we'll take a look at. It's a game. I see it uses some kind of recursion. Then we will take a look at TL-Draw Computer, which is a pretty impressive project. It looks a lot like Orion Reed's experiments. He has this automation tool that he posts as GIFs to Twitter, and this feels a lot like his experiments, but actually productionized. We will take a look at this in a moment. And there is some lecture that I wanted to take a look at, that we'll take a look at together. Okay, so this is the plan for today. Slowly. Okay, there is some text here. We'll actually read the text using Alltalk. This is a TTS engine that I'm using. There we go. Generate TTS.
Drosta's lair is an unusual programming environment for building and counting mathematical structures. Built in a 2-week sprint, in Drosta's lair, the user manipulates mathematical structures through direct interactions, dropping dominoes on chessboards and dragging items between lists. The system's power comes from 2 forms of abstraction on top of this foundation. An AM mechanism that allows strands of execution to branch from one another, and a procedure calling mechanism that enables recursion.
Okay, Drosta's lair is Swords and Sorcery style point-and-click adventure. Okay, we will play through the walkthrough. The title of the first chapter is called Reversal of Fortune. So this is the interface. I really like the interface because it uses very strong textures, it's consistent, and there is this principle in design that whenever you pick a color, you should always show this color not in one place, but at least in 2 places in a scene. So every color should not be just standing there alone, but have some kind of counterparts. And this is the case with yellow here. There is yellow on the text in this corner. The cursor is yellow and there is the candle. We have this purple color, which again is in a couple of places. Looks really nice. A piece of parchment is against the dungeon wall, dimly lit by flickering candlelight. On it is a list, A, B, C, D. Maybe let's play some medieval music. Oh, that's loud. Okay, I will create a couple of them. That should be more fitting. Our teacher who is also a cool wizard has tasked you with reversing the elements of this list. You first try to do this by moving elements one by one, clicking an element. I have no idea what's happening, but I know I can hit Ctrl Z to undo. This is not a way to undo this thing. I guess we can create a new list. C should go here, B should go here, A should go here. Okay, we have reversed the list. Now what? Okay. Clicking an element picks it up and reveals places it could go. You add it to the start of the second currently empty list. I think we went through this. They went from the start, not from the end. When I work with a list, typically we operate on the head. Each list has a head and a tail, right? But because I work in C++ all the time, for me it feels natural to start from the back, because if you have a sequence of elements continuous in memory, not a list, not a linked list, but a stack, then it's more natural to just grab objects from the end. So this is my intuition. Yeah, mathematicians would probably grab the first element. Our action has magically created a second square of parchment on the wall, showing its effect. You could almost think of this as a comic book, though the damper and clink of chains in the distance make the situation anything but comical. Let's try Lazel's voice.
You could continue moving items one by one, and it wouldn't take long with a list this short. But you know that sooner than you would like, you will face far greater foes. Moving items by hand, you'd only make it through a handful of items before being knocked out by some Orcish cudgel. You need a way to automate these motions, a sorcerer's apprentice of sorts.
There was a poem, I think by Goethe, called Sorcerer's Apprentice. In this poem, yeah, the sorcerer uses its... I actually don't remember what's happening in the poem. But I know there are some interesting issues happening.
The spell to cast has been with you the whole time. In the top left, this sigil marks the script you are writing. With it, you can take what you've done so far and cast it again as a spell of its own.
Okay, so let's undo. Okay, because we are accessing item 4, this is causing an issue. We have to move from the head. Okay, now we can create a sequence of calls. Hey, this is really nice, actually. We can move one element and then recursively call this again. I like the metaphor of dungeon layers. Each level of recursion descends one level into the dungeon.
Portals into the wall have opened up. Deep holes with deeper holes beyond. Inside each hole, the sigil does its work. So each begins with the start parchment, and then has a move itemment, just like the script, outside the hole. But each starts with the outcome of the previous hole. So while the top level moves an A, the next level moves a B, and so on. Where will this madness end? At the bottom, in a fateful encounter with the eldritch consequences of your sigillic incantation. The base case. You are never far from it. A short pan takes you over to the deepest hole, 4 levels below the surface.
I should have a shortcut that will do this work.
In this deepest level, the first list has been exhausted. All items have been moved to the second list in reverse order. This is great progress. But we're not done yet. Though our answer lurks in the depths of the thirks of holes, nothing is coming out to the surface. Yet. The problem is that our parchment is getting stuck. The spirits of the parchment call out to us. List is empty. We know that, actually. The first list being empty isn't a problem at all. It just means that we are ready to call our answer back from the world of spirits. So we guide the parchment along by giving it an escape route. Clicking the double dagger mark creates one.
Okay, and this is it. When the list is empty, so here we have no result, right? We have to specify what is going to be the result here. So we can say that when the list is empty, we will just return this list.
The escape route guides the parchment from the deepest level, where it ran into the obstacle of the empty list. At each higher level, the escape route is available, but the parchment doesn't take it since it can happily proceed through the item movement and the recursive core. At last, we have a final answer on the far right. Our strange recipe is complete. We are ready to face far larger lists and the monstrous beings that might bring them to us with nefarious intent.
This is actually something very cool. It's that you can see there is no control flow. The only control flow that we used is sort of an exception handler, where if an exception happens, we can specify a custom logic, which in this case causes a return. We could probably, instead of causing a return, for example, reverse the list again. Yeah. Can I... It would be nice if I could call this subsection of the code. We went too deep. It's Stack Overflow. Let's try the second one.
You've done well in your first test, but your teacher reminds you that you are still a novice. The greatest spells dissolve the bounds of decision. These spells, when confronted with the question yes or no, respond yes and no, becoming the branching limbs of a tree, reaching ever towards an infinite sky. To learn this art, you take upon a simple task. Generate every face card in the deck. You begin with the raw material, a list of ranks and a list of suits.
Yep, there we have it. A face card is formed by combining a rank with its suit. So first you pick a rank.
You do this just the same as when reversing the list. Pluck out an item from the list of ranks and add it to a new list. So you've picked a particular rank. But that isn't what you really want. You really want to, you know, dissolve the bounds of decision and pick all possible ranks. To do this, you click the Move Item 1 heading. It cycles through a few different headings. Move first item, move last item before landing on move any item. That's the ticket. Oh, there's a stack of 3 parchments, 3 parallel universes of action. They're fanned out because you're hovered over them, but moving away for a moment shrinks them into a compact stack. Finishing the job means doing the same thing with the suits, creating branches on top of branches. You pick a suit off one of the panels on the right and put it next to the selected rank.
What do we have here? We have all kings, all queens, all valets. Nice. So I like the interface of this approach to kind of compute. However, I think it works nicely in small cases where all of this stuff fits in memory and fits on screen, and it's the thing with unrolling execution on screen. It works well as long as the execution doesn't actually involve massive amounts of data or very long sequences. So it's a cool approach. I think it would be hard to apply it to bigger problems. Because that would require very careful coding not to kill the performance. Next one is the enumeration.
You've learned the rudiments of casting recursive spells and splitting worlds into swarms of possibilities. Now it's time to put these arcane arts to use on a real challenge. An evil sorcerer is tormenting a nearby village with an insidious puzzle. How many ways, he asks? Can a Tuzin checkerboard be covered completely with dominoes? What? And isn't a number? That's a letter. There's no chance you'll be able to grapple with this sorcerer's pretending letters and numbers hocus pocus quite yet. But you can start to get a feel by replacing n with a number. Let's say 4.
Okay, this is our checkerboard. How to fill it? Well, you can try just putting a domino down. Here are dominoes, I guess.
Now maybe we could fill the rest of the board with vertical dominoes like this. You realize you want to repeat a step over and over again. Sort of like the reversal exercise you were trained on. But this is a little different. Before, you casted a recursive spell onto an entire panel of parchment. Here, that would cause the next dominoes to stack on top of the first domino in the same squares over and over again. We need to cast the spell so that it acts on the rest of the checkerboard, leaving out the first domino. Maybe you can just point your wand over a little?
Oops. Apparently it makes a difference where we chop this. So when we cast this spell onto the subgrid, it fills the whole subgrid. However, it very quickly fills the board completely and stops. Okay, so this is our board, filled with just 2 motions. We placed 1 domino and applied this recursively. Okay, let's place 2 horizontal dominoes. and cast our spell.
Once again, you're left with board to fill after your first 2 dominoes. You decide to once again cast a recursive spell, assessing your top-level procedure how it might choose to fill the remainder of the board. You expect to get another simple loop, showing how 2 more horizontal dominoes could be added to fill the board. But something extraordinary happens.
Yeah, we get like proper branches. It tried to add vertical results. I think here we should somehow combine multiple results. Oh, this is happening automatically, nice. Well, this is pretty cool.
The 2-way branching you defined at the top level has been replicated inside every level of your recursive spells. There are no simple 1-way loops anymore instead. With every deeper hold, there are new branching possibilities. You check the final output. Giving it a bit of thought, it seems like these 5 coverings are the only ones possible. Have you somehow stumbled onto a fully general program? It's difficult to make sense of it all at once. Fortunately, your teacher taught you a collapse caused beyond depth, 1 spell hitting 2 on the keyboard, so you use it now. A great many of the holes before you shrink, leaving only the highest level structure visible.
Nice.
Of course. After adding a vertical domino, you can add either a second vertical domino or 2 horizontal dominoes. Similarly, after adding horizontal dominoes, you can add either a vertical domino or 2 more horizontal dominoes. It does seem like following this branching pattern. Always adding either a vertical or 2 horizontal dominoes would get you every possible covering. You've conquered the problem of the 2 or 4 checkerboard. But some mysteries remain. What did that evil sorcerer mean by N anyway? Finding out will be journey for another day.
Okay, we have a longish discussion of the background, and that's pretty amazing. Can we TTS everything? I hope it doesn't have a limit on the length of the text. I finally found a good prompt. It has to include classical. So this is indexer. Oh, the text is too long. I have to cut it. Still too long. I've restarted all talk. Let's try now. Let's try now. This takes way too long. I know what this might be. This may be the clickjacking protection. Or not. I have no idea. Strange. I will give it a moment to restart, and then we will try again. I have no idea why TTS is not working now. I know I pasted too large text and it just stopped working. Let's just take a look at the explanation. I think we can resume the regular music. So normally when I kill all talk, it should automatically restart. Oh well. Okay, I see. So whenever I look at any sort of functional programming, I think it works super well in small examples, in small cases. But whenever the problem becomes more complex, when it becomes comparable with the capabilities of the computer, when you're starting to push what you can do, I think then functional programming becomes problematic. Programming is a lot about managing two resources, time and memory, like scheduling computation in time and planning computation in like computer memory. How do you fit the computation? And I think since computers are fundamentally procedural, they execute a sequence of instructions. So I feel whenever you have to actually exploit this fundamentally sequential structure, you just have to break through the abstraction of functional programming and implement something that would be sequential. That would, instead of, for example, elegantly recursing into every case, you would have to change the recursion into iteration so that you finish earlier. So Marcel Gethal's recent subsequently prototype offered an exciting alternative to this functional nested scope vibe. In subsequently, each comic pane contains the full state of the world at a point in time. You act directly on pane's contents. There are no variables buried in some other pane. Everything you need is right where you are. Subsequently is the proper name. Also demonstrated that some processes, like picking elements out of arrays, feel more natural as imperative process, which mutate a world state rather than as functional processes. So yeah, this feels very much like this game. Subsequently, its lack of spooky action at a distance and its imperative model felt appealing to us. They added up to a physical feeling that seemed appropriate for a live interactive visual programming system. Also, they were weird by conventional CS standards, which is always a good sign. In order to extend the subsequently model to work for construct and count style counting problems, we had to add branching. Sure, subsequently had conditional branches, as shown in the shot above, but we needed unconditional branches that are taken simultaneously, dissolving the bounds of decision. This sounds fancy, but it's straightforward to build. It is also well-trodden ground in computer science, also known as AMB or the least monad or non-determinism. Admittedly, it's less common to see this kind of thing in an imperative environment like TTS-ed, which is exciting. Actually, I'm not familiar with this at all. What is AMB? Okay, so this is a branching instruction. Okay, AMB is a very interesting thing. I think it relies on throwing exceptions or something like that. And restarting execution using each value that can be passed. The subsequently plus branching portion we brought up was enough to cover some simple counting problems like the cards made in the ever-branching walkthrough. But some of the most interesting counting problems were still out of our grasp. These were the ones involving recursion, where counting possibilities for a larger structure involves splitting it into pieces, counting possibilities for each piece, and then recombining the possibilities of the pieces into possibilities of the whole. I have to admit that in Automat I am not even considering the same kind of problems as they do here. I think these kind of problems, they are mostly interesting to mathematicians. I mean that you rarely encounter them in day-to-day. I mean, if you're programming, yes, you encounter them all the time. But if you want to implement like a simple program to do something, it rarely has to do recursion. Usually, following a sequence of instructions is 90% of programming is just following a simple sequence of instructions. So, going back to the article, in the walkthrough, we showed how to use recursion to count ways to cover a checkerboard with dominoes. We were actually originally motivated by a more complicated question, counting paths of the fractal Sierpiński graph, also known as the Hanoi graph, since it maps out states in the Towers of Hanoi puzzle. We weren't able to get to this problem in our short sprint, but dominoes were a nice alternative. Okay, so this kind of stuff. Aside from the applicability of recursion to counting problems, we were also just plain curious about how to make recursive structures comprehensible in a visual programming interface. Elliot in particular has been investigating this strand for some time. Yeah, I think this is important. I think for some problems, nothing beats recursion. It's like a completely different area just from what Automat tackles. So with that, we had the basic formula for the programming model in Droste's layer. Subsequently, style imperative flowcharts plus branching paths plus recursion. That's basically it, as long as you ignore, as we do for the moment, that Droste's layer is also a point-and-click adventure game. Branching. So, I think the biggest improvement to this game would be to combine the tutorial and the game itself, so that you don't have to switch between two tabs. Branching. Droste's layer provides two ways to produce branching computation. Invoking multiple actions or procedures of a single panel. Invoking an action or procedure that has multiple outputs. Yeah, so you can perform several different moves, or we can do this all option. When multiple distinct actions are invoked on a panel, they are shown branching from it. But when a single action or procedure has multiple outputs, we group these outputs into a stack of panels in the interface. it would have alternatively been possible to not group these outputs and to instead display them as branching paths. It's just more compact. There is a trade-off involved in putting multiple outputs into a stack. The stack visualization we chose keeps the interface closer to the structure of an underlying flowchart. Each action added by the user is depicted in one place. If move an item action, like it instead produced branches in the interface, these actions would be depicted multiple times, making the interface less directly match the underlying program. But in some ways, the runtime behavior of the program would be more clear. This tension between highlighting static and dynamic structures is common when building live programming systems. The dynamic execution of a program is an unfolding by loops, calls, and slicing, by conditionals of the program's static specification. It is challenging to show that both static and dynamic layers at once. But there are techniques that can help. Thoughtful visual design can go a long way, and lucky for us, computers are interactive, so we can use interactive techniques too. A future work on Droste's layer could let users switch between stacked and branched views as they please, or perhaps hovering a panel could reveal, through highlight, other elements on the screen less obviously connected to it. Recursion. What I really liked was the way to end the recursion chain with the cross, because that was like... I like it because it was a type of recursion that doesn't require an explicit stop condition. It just... When you find an error, you can say, okay, just throw the result out from here. There is one case I think which could be problematic in this approach, or not problematic, but I don't think there is a way in Droste's layer to end the recursion without returning a value. And I've also seen there is a way to combine values. When the two paths joined, there was a circle here. I didn't click it, but I've seen there was some option to combine return values. Yeah, so the reason I don't like recursion so much is that it causes the memory to explode. I mean, when you start recursing, you lose control of the memory usage. And memory, like I said, is very important. I feel if there is a holy grail visual interface to programming like classical computers, not quantum computers or anything like that, then memory management is going to be important. And because memory is not infinite, and like memory management is key, memory should take space on screen. There should be no invisible concepts that take exponential amount of memory. And function calls and recursive function calls are something like that. These recursive function calls essentially cause possibly exponential memory usage. Putting wild alternatives aside, it was our job to bring recursive calls, procedure calls in general, into the subsequently model. In subsequently, an action is presented as a comic panel that shows a picture of the word after the action, annotated with graphics that illustrate the action itself and descriptive text above the panel. We took this design and extended it to our depiction of procedure calls. Calls in our system are represented as a whole containing the body of the called procedure, followed by after the procedure call action panel. Also, the symbols that they used are kind of nice for recursion. I think this is a symbol for twins. No. This is a chemical symbol, not a zodiacal. I have no idea. No, this is a zodiacal symbol. Cancer. This is Cancer. Note on how we visualized contents inside of holes. The most straightforward move would have been to show a called procedure operating only on the piece it was given, without any reference to the parchments or the larger hole they came from. But we reckon that doing this would give up a lot of the physical object parchment feeling that we were striving for in our design. Passing into and out procedure calls would require a reorientation. To maintain the feeling of grounding we wanted, we instead choose to always show parts of the contexts of the whole. We use a color-coded outline to show what part is actively focused by the procedure call, and fade out the rest. Oh, I see. Yeah. And this is what I mentioned about the colors. We maintain a conceptual color scheme throughout the interface of Droste's layer. Yellow for actions. Yeah, so the stuff that you do manually. This text here, your cursor, the candle. Purple for procedure calls. Yep. And red for trouble. This is very good. A very nice idea. It makes this whole thing feel more consistent. This is very subconscious message. I think when using the interface, often you don't even realize that the colors actually help you navigate it. Although we've tried in this project to visualize recursion as concretely and understandably as possible, building a recursive procedure is still an immensely programmer-brained activity. It won't feel natural to most people, even with our visualizations. But we aren't ready to give up on recursion yet. What could we do to make building recursion in our system less programmer-brained? Maybe users could start by building concrete trees by hand, and then our system could help them build recursive functions to match this. This is an interesting idea. Automatic recursion. Yeah. automatically discovering the rules of recursion, it feels a lot like a quantum computing problem or some NP-complete task. You know, where you have to iterate over all possible programs and see which ones produce these kind of results. Conditionals. I've seen only those conditionals where you can handle an error, but maybe there are more. Yeah, this is nice. I mean, it doesn't feel right in the sense that it doesn't feel complete, but it's definitely a cool and a very elegant idea, this escape idea. It looks like a very nice game also. The aesthetics are amazing. It's very nice. Yeah, so I guess this wasn't meant to be like a proper, like, finished game. It's more of an experiment. This is what ink and switch does. But it feels like it's sufficient to make a game out of this. It's already nice enough. I think there is plenty of stories that can be built with those basic tools already there. And if you look at some of the typical programming problems, you could probably design a whole campaign out of, you know, simple programming problems, maybe getting more and more complicated as time goes on. And there was also this game where you were an alchemist and you were assembling chemical compounds. So one thing that game did, I don't remember the name, was that once you assembled a chemical compound, you could reuse this kind of recipe in your subsequent missions. So this gave you a feeling of progression, of building a library of blueprints that you can reuse. I think this is a nice thing to have, this library of blueprints that you can carry on throughout the game. I mean, if somebody wants to make a game out of this, I can... by game, I mean something with like a long campaign and this kind of stuff. I think the authors are more interested in actually developing the computational model behind it, which is probably a better objective than making a game out of it. I have to say, this is probably the best visual implementation of a functional programming I have ever seen. Yeah. I don't think anything comes close. Blueprints, maybe. But I feel this is more capable than blueprints. Or this could be more capable. The ideas here are better. By blueprints I mean those data flow nodes, nodes and arrows. And those nodes and arrows, by the way, this is another functional, another implementation of the functional programming. So this is, I think, a more interesting interface. It's definitely better for combinatorics because you can do this splitting recursion, which is very difficult in blueprints or blueprints. In node and wire interfaces. Okay, very cool. I have to bookmark this. I have no idea where. Let's put it here. I have to organize my bookmarks. Okay, I'll make a short break and then we will resume with TL Draw Computer. Okay, I did take a look at TL-Draw computer before, so I know how it works. Okay, this is not a sorting machine, this is not my sorting machine at least. So what we will do today is we will take a look at some examples instead. So the way TL-Draw computer works is you have those text blocks so each block, which is connected by arrows to other blocks, can look around and analyze the contents of other blocks. There is the idea of running a block. When a block runs, the text copies itself to all the nearby text blocks and schedules the next block. Instruction block, when executed, looks around. It takes all of the input text and it uses them as contents to execute this task, the instruction. So it will write a short commercial about Nike's new AI-powered smart clothes. The result of instruction is written in the output. So this is the result. Text can be TTS-ed.
Experience the future of athletic performance with Nike Smart Gloves.
It can be used as a prompt for an image. And this, if I remember correctly, this is a switch. So it's something that blocks execution. Switch? No, it's just a button. Anyway, when you press this button, I actually had no idea you can regenerate text, like speech, like that.
The glove whispers promises of peak performance, a future sculpted by algorithms. It speaks of maximized potential, of reaching heights previously unattainable. It promises elevation, but in the quiet of the night, the echoes of unfulfilled dreams resonate. Each swipe, each press, a painful reminder of what might have been. The technology judges, and the judgment is relentless, exposing every flaw.
Actually, I wonder where is it taking the source text from? Because when it's doing this speech block, is it audio to audio or does it go through text? It has to go through text. Because on the LLMs will do higher level, like this kind of processing. So I think there are some conversions involved. It's very interesting that you don't really see what models are invoked and where. It looks like, hey, it's speech to speech with some text input, but behind the scenes there is probably either this text is somehow smuggled into this speech block, so it's invisible, or there is speech to text involved, and we have some, I think, hidden LLM being invoked to execute this prompt. So there is actually quite a bit of hidden logic happening here. Yeah, my sorting machine unfortunately got overridden by a different program. Oh, there was the sorting machine. So we have some instruction blocks. and a switch. Yep, this is a switch. Or maybe not. No, those are conditions. I was trying this before, and the interesting thing that happened was that the format of the list was slightly different in each time the instruction block was executed here. So because sometimes it was adding commas and was doing a list on a single line, sometimes it was adding dashes. Oh, it repeated itself. There is this mechanism as well, where you can insert a toggle and disable it. So because this instruction, it can look at anything that points to it, even through disabled switches. But when this text is executed, actually I have no idea how it's added to the list. So that it's appended instead of replacing the text here. Let's try an X-ray machine. Let's try to find some Automat textures. Okay, here we have our design. Okay, it's not a super X-ray, but the image was probably out of distribution. What else we could pass? We could change the image to the flip-flop, maybe. Let's try this one. We can also try passing the mouse image. Yeah, this is just crazy AI. Sim Battle Simulator. It's a fun way to chain simple LLM prompts. Okay, this is going to be interesting.
The Great Sun Lion War, a script. Upon the plains of existence, a colossal conflict unfolded. 1 trillion lions, a golden tide stretching to the horizon, roared their defiance against the incandescent sun, a celestial behemoth blazing across the heavens. Lion 1, for the pride, for the plains. Lion 2, ferocious growl, we will not yield. The lions, each a creature of immense power, their combined might shaking the very ground, launched their assault. Their claws, sharp as stars, raked against the sun's radiant surface, but their attacks were met with a searing inferno. Sound effect. Intense roaring, clashing, and fiery explosions. The sun retaliated with blinding light, a storm of solar flares that incinerated swaths of the lion army. Yet, the lions pressed on, their sheer numbers overwhelming. Lion 3. The battle raged across the sky, a terrifying spectacle of fire and fury. The lions fought with unmatched ferocity, their numbers seemingly endless, but the sun's power was unyielding. Sound effect. A crescendo of roaring explosions and the sounds of immense destruction. It was a battle of attrition, each side sustaining unimaginable losses. Finally, as the sky itself began to crack under the strain, a stalemate was reached. Exhausted and with countless casualties on both sides, both the lions and the sun retreated. The battlefield remained smoldering, a grim reminder of this epic, unwinnable clash.
Well, those are LLMs. It doesn't make much sense. A retro website showed the patch as an image, 64 pixels square. In line with the header, the site should display information for each launch in a table with links in an ordered list below. Oh yeah, it has a blog called Website that can be used to generate websites. Wow, this is interesting. Let's check this one. Oh, casual professional, okay. Wow, this is nice. So this is purely text processing, but it shows you subsequent. It gives you an option to do multi-step kind of improvements. It's a whole sequence of LLM commands. Very nice interface and very readable. You can see all of the intermediate steps. So we already looked at the sorting machine. Next is story generator. Actually, this is something that I find super interesting. I attempted this myself. Who is the character? Okay, I gave it some ideas to write a story. Here we have an outline. It's not what I had in mind, but it takes the story in a slightly different direction. It describes it from the perspective of Sir Roderick. I think, yeah, this was the main character. I was thinking more of Sir Roderick being the cause of the ship's disappearance. Chapter 5? What? It clearly skipped some chapters. Oh yeah, because it probably thought that the story is not finished here. Because this was a very high-level idea. Also, this was the problem I encountered with LLMs. They are often giving very generic stories, and they do everything they can to avoid giving you the details. This is a very similar problem that image generators used to have. So if you look at the old approaches to image generation, the problem they had was that they always kept generating very blurry images where they couldn't decide on a single idea they want to show, and they kept showing you just an average of all of the potential ideas. I think language models have a very similar problem, and I feel like the solution for language models is going to be identical as to image models. It's going to shift from the expectation maximization to denoising. So it's a slightly different training objective, where instead of trying to optimize the model to output the best probability distribution, you will ask the model to iteratively improve the output by removing the noise, and to actually turn it from something blurry into something very concrete. I think this is what will make models, like textual models, very good at text generation. Maybe we'll take a look at that. If I have some time to play with ML on stream, we could try this. I think one thing that helps is to constrain the... okay, there is this issue of skipping chapters. One thing that helps, I've seen, is using grammars. Yeah, but... So I think there are still some utilities which are used in LLMs a lot, like grammars, missing from this tool, but otherwise it's very nice UI. So a grammar can force a model to start this section with chapter 1, this will be chapter 2, and this will be chapter 3. To avoid this effect of skipping chapters. Tricycle plus octopus equals 11. That's nice. It's a good one. Okay, I don't have a camera connected to this computer, unfortunately. Oh, it's still making a website.
Bad Nintendo says,
Hey, Hope, all is swell dropped in to check in. Clock me out while joking, but good to see you are still streaming when able.
Hey. Yeah, we're slowly going. I mean, it's like one step forward, 2 steps back. We're not coding today. Automat is in a slightly broken state, but it works. We have no text. I looked at the performance, I can fix everything, but some things that used to be broken now work. Like I can delete objects. That used to be broken because we had multi-threading, and deleting objects caused them to be access of invalid memory in other threads, which is no longer the case. So yeah. I think I will fix this before the new year, and next year we will add something cool, some cool new feature to Automat, because I'm a little annoyed by kind of spending so much time on this rendering infrastructure.
Making an OS or an application?
I would say it's closer to an OS. So the point of Automat is to run on multiple operating systems and to allow you to do the same kind of stuff that programmers do. Eventually, in the future.
Good.
We are in a very interesting position with Automat right now. So when we render stuff, all of the rendering commands we're actually serializing, and we have those command buffers that can be kind of sent and executed on a different machine. So I'm actually thinking about doing this experiment with where is it? With remote rendering, because it's not that far off. So we could essentially have, this is actually something that's very useful when doing automation. So when I was playing some games with Automat, one thing that was a problem for me was when I wanted to tweak Automat code a little bit, I had to keep alt-tabbing, like quitting the game, not quitting, alt-tabbing out of the game into Automat, doing some fixes, then going back to the game and seeing how they work. And I think it would be much more convenient to have a different computer, or maybe a smartphone, where I could adjust some things, for example, the timing on a timer, and then it would influence the execution of Automat on a remote machine. So this remote rendering would be very convenient to have for desktop automation, for game automation.
So X and Y starting position of mouse.
Yeah, I think mouse, doing gamepad. So right now Automat can automate keyboard decently well, but mouse is terrible, and gamepad is non-existent. I think we could tackle those. I think mouse might be easier. I will think about this. I've also been thinking about decisions about logic. So any non-trivial program will require some kind of control, so that you can make a decision whether to follow this path or that path, or loops, this kind of stuff. Right now it's not possible in Automat. You can create a loop. Don't pay attention to performance. You can create a loop, but you cannot create a branch. Yeah, we are missing so many things that I don't even know where to start. Yeah, maybe automating mouse movement will be a good project for January next year.
Use both touch and mouse pointer on that bird, so you can hover over an application and touch the screen, and close or power it off auto.
Yeah, I'll have to think. So there is this idea called MVP, right? So that the idea is that we come up with something that's practical, something that brings some value already. I think this is kind of already there. I think Automat can already automate keyboard actions. We've probably run out of memory. There's probably some memory leak somewhere, who knows. So I think we have it. I think right now we can build upon this. So Automat can already play games like Nintendo games, for instance, Super Mario Bros. Yeah. I think mouse and keyboard okay, maybe the most annoying thing is the inability to... So when I record the macro, again, don't pay attention to the performance, it's broken right now. It would be nice if I could adjust those timings, for instance. So maybe improving the timeline would also be a good project idea for next month.
Okay, man. Enjoy go back to focus time. I want to see it finished.
Sure. See you around. Let's look at more TL draw kind of examples. A recipe generator. Okay, that could be useful for me. I am totally inept in kitchen. Chocolate, dry ice. Okay. Create a recipe using all of these ingredients. Maybe not all of the ingredients, but it would be nice to have a utility that I can just make a photo of my fridge contents and it would come up with something to eat. This is probably dry ice. Who has dry ice? Dry ice is the frozen CO2, right? Ingredients: dark chocolate, heavy cream, which is not in the ingredients list. Dry ice pellets. Looks interesting. I think with some tweaks, this could be useful. I really like the TL Draw computer. We also have Animal Lab. Let's look at Animal Lab. Write two different animals. You're a mad scientist. Combine these two things into a new hybrid animal. I think the proper term is chimera. Let me open the English Wikipedia. Chimera, a single organism with cells from two different zygotes. But I think hybrid is also... Yeah, it's also a good term. Nice. I think this could be applied to Pikachu. Similarly to Pokemon, just as well as to real animals. I think I've seen a game like that. I'm still waiting for an X-ray. Okay, it's not exactly the same animal. Not as nice. Okay, amazing. So today we've seen two completely different future of coding approaches. So Droste's lair is my favorite, I think, functional environment. Or like, I think this is the best implementation of functional programming I've seen. I still think functional programming is not like the best approach to just driving computers, because it doesn't translate well to how computers work, under the hood. It tries to hide their true nature. And we also have a TL-draw computer, but nonetheless I still like Droste's lair because how well it kind of translates math into visual programming. And TL-draw computer it's a really fun, really simple way to control LLMs, to build pipelines out of LLMs. Nice. Okay, the next point on the list is actually a lecture, which is almost half an hour. I will turn the music down a little bit, and we will play it, maybe on a slightly higher playback speed.
Quick introduction on incremental graph code, otherwise known as IGC. IGC was thought of as basically trying to solve a problem. There's two main environments that programmers are using.
It's very quiet. Let me look into that.
Hi, my name is Max Watson, and I want to give a quick introduction on incremental graph code, otherwise known as IGC. IGC was thought of as basically trying to solve a problem where there's two main environments that programmers are using. One is the typical one.
Okay, I will ramp this up a little bit more.
Integrated development environments, where you basically write top-down in linear fashion a whole bunch of text in separate files that are sorted by different folders, packages.
Sorry, you have to amplify the sound on your end.
IGC was thought of as basically trying to solve a problem where there's two main environments that programmers are using. One is the typical one that's seen in industry, which is text-based IDEs, or integrated development environments, where you basically write top-down in linear fashion a whole bunch of text in separate files that are sorted by different folders, packages, and whatnot. There's many different IDEs or text-based environments grouped them together in this case, but a lot of the advantages really come from the complexity management, where you can, like I said before, store everything in files. There's a lot of premise because this is the norm scene, and there's a lot of tools that are kind of built around this thought to handle complexity management. On the other side, you have incremental programming environments, or IPEs. Incremental programming environments are, for example, a REPL that you see in IPython on the left here, or even on the right side, you have Jupyter Notebooks, where you have documentation and cells. One nice thing about incremental programming environments is that each step is built on top of the last in very small segments. So for example, if you want to build a project, you don't have to have everything there and just click run. You can build it up and see where things go wrong on your way towards finishing the project. There's a lot of benefits. For instance, if you want to do some testing, if you want to maybe explore the effects of one code snippet versus another, or potentially you want to figure out and solve a bug without recompiling the entire project. So the idea that was kind of in my mind was, how do we bridge these two environments? How do we get the complexity tools and the typical kind of things that people are familiar with in industry from IDEs, and how do you get the incremental programming techniques and exploratory kind of aspects from IPEs? So this is where we kind of write down all the main advantages from each. So on the IDE side, we have large files, code bases, we have very big structure behind everything. Readability is a core component, and how to actually understand the code. Extensibility, users are able to make different extensions and kind of build on top of previously had tools. And integration with version control. How can you put this into like a Git environment, and how can you collaborate with others into a big project. The other side, incremental programming environments, they allow you to run and test small code snippets very quickly. You can see the feedback immediately, which is very much the essential component of exploratory programming. You also have documentation that you see in Jupyter Notebooks that allow users to share their ideas and create a narrative behind some example that they're trying to demonstrate. You also don't have to recompute the entirety of the project. So the idea that we came on kind of a middle ground is let's make the entire code base a graph structure. So what do I mean by that? So here we have kind of a very snippet of IGC, where you have different type of nodes, and you have a whole bunch of different relationships that have meaning between how these nodes are executed, the dependencies, and what they relate to. So for instance here, we see the blue relationships here are representing the execution of the code itself. These orange lines here are representing what nodes are dependent on other nodes, as well as this red line here and the pink line is what nodes are attached to specific nodes. So you have potentially a class node that represents an object-oriented paradigm. You have methods that are attached to these classes. Or you have normal code fragments. Or you have nodes that represent library functions. Or you have documentation nodes that are attached to a specific code fragment. We'll go more into detail on a lot of these nodes. Here you see the entire interface, or the UI, of IGC. We'll go more into detail on every single component and what each means. But as you see, we have selected this one code fragment, and all the data
Petiraj says,
Yo, what's up,
are
Barrett?
corresponding with their outputs,
Hey,
documentation, and different views.
so today we are not coding Automat. Today we are looking at recent developments in future of coding. So we took a look at two so far, which were both incredible. The last one is a presentation about, it looks like somebody's PhD or something like that, or somebody's research. So they are representing execution as blue arrows, dependencies as yellow ones, and
Corresponding with their outputs, potentially errors, documentation, and different views.
yeah. Yeah, no, we will see if there is anything interesting here. So far, it seems like it could be.
So to go more into IGC on how it was built, it's actually an Electron web app where the front end is using React, TypeScript, using React Flow for the actual graph itself. On the back end side of things, we have a Node.js, also with TypeScript, which handles file operations and the code analysis. Node.js is very nice because potentially we can port this into a VS Code extension. Electron is specifically used versus just having a native web app, so we can bundle everything together into a system application that works for every operating system. And the reason we need this as well is so we can actually use native file functions such as directory selection. We also, if we want to completely forgo the Electron side, the front end web app of everything is already made, so we can convert this into a cloud application, similar like a lot of Jupyter Notebook instances are being held. Currently, the environment only supports Python, but in theory, this should be completely language agnostic. Users should be able to completely create the type of nodes that they want, specific to the language that they want as well. The idea also behind IGC is that this will be completely open source and community focused, so everyone can build extensions, everyone can build custom components, and they can import it directly into the project. Let's quickly go over the UI in a demo. So first you see here on the left side, you have the file navigator. The file navigator looks exactly
So in the previous slide, there was this
so you can select
small graph, which was, it perfectly shown what's the issue with arrow-based interfaces. It's just a mess of connections.
very similar to a normal IDE.
Colors help a lot here.
As we click,
It was actually more readable than most
output,
environments I've seen
and as
because of colors.
the editor will detect automatically what type of file it is and format everything correspondingly. If you click an IGC file, you have this. This is an empty IGC file with its corresponding data. You initially start with a start node. We will get further into what a start node is.
Fun thing is that Automat's internal format looks very similar to this.
Blank new node. Initially, it starts as a base node. If we want to execute some code, for example, we'll make a code fragment. But we can also do any of these other types. Do a code fragment, we can rename it, say first code. After we do that, once we select it, we get a new view called the code node view. we see here, there's a little icon where if we double click, it generates another node. This node is a documentation node. That is
Okay.
double click. We see here, there's a little icon.
Okay, this is for documentation.
It generates another node. This node is a documentation node that is attached to this node that we created. Let's say we want to put down some markdown. So this is a sample markdown. And then as we click away and on this node again, we get the corresponding markdown that's associated with this first code node. Let's do quickly a sample prompt. All the language currently is already
So the documentation disappears when you focus out of this element.
language specific. You can do any single language that you want.
It's nice, actually, how the documentation is shown.
Click away. This is all saves now if we do Command S. And now, let's try to execute this code itself. So we're going to do start new session, and we'll name it just session 1.
So many forms.
As you see, a new session on the left side under the session configuration is now done. Let's execute this node. So we will execute it. So you see when we create that session, now this is enabled. We run it. We need a quick update. So you see there's an arrow from the start node. It's all states, all starts from this one start node. That's an empty null state. But now, since we executed this, it's coming from that initial null state and coming to this first node. If we look now, this is updated where we have an output terminal exactly showing what the standard output is. We also have a standard error and standard or a configuration. So we can see all variables are defined by this node. We also see metrics in terms of...
Okay, I will point out something totally orthogonal to the contents of this presentation. It's that the user interface, it uses a visual system designed for very old version of Android. I think Android Honeycomb. Or maybe not Honeycomb, maybe one of the later ones. I think this is a maybe it's a very early version of material design. No. What was the name of predecessor of material design? Maybe it's material design V1. Yeah. This is the style. Those colored buttons, the tabs are very indicative of material design V1. Anyway, this is totally orthogonal. Let's continue. So I've seen that this arrow appeared implicitly. It wasn't drawn explicitly by the user. He just said that, hey, let's execute this block first, and the arrow appeared.
What session this was attached to. So let's quickly make a second node. We do a little bit more complex things. We're going to create some variables so we can show how the configuration changes over time. So we're going to just define some public variables, very simple.
Coming up with titles for every node and like filling those forms. This could be improved a lot. I think instead of picking from a list, you could, like in Automat's toolbar, I just select one from the toolbar. And names, maybe LLM could caption blocks or something like that, just to make the execution faster, because in IPython or like with Python notebooks, when you execute there, you just write the code. You don't have to like describe anything. This is why it's so convenient to work with.
And then we can do C equals B. No. A. And let's see the output of this. So now we're in the same session still. We'll execute this. Suddenly we see the configuration, the global configuration here has changed. If we look again, we update this. So there's no output.
How was this executed? I missed that.
Execute this. Suddenly we see
Okay, so when he pressed this arrow, a connection appeared.
update this. See, there's no output because we're not putting anything to standard out. But we have no errors. The configuration has changed specifically for this one. If we go back to the previous configuration, we see kind of a snapshot of what this node had. But this didn't create anything. It only had its one output. The state is carried over from node to node. So we have an updated timeline of how state is changing. If we look further into different UI components, we have very basic settings here. We have edits configurations. We have also project data. We can also change if we want the theme to a dark mode. We're going to change to light mode, and it's more visible. Like this. We have filtering options to be able to see specific relationships that occur.
I think those implicit sequences being converted to explicit arrows, this is a really cool idea. I think this is what allows you to turn, just a random graph of random objects into something like IPython, which executes deterministically.
And we're able to play the entire session again if we so choose.
Nice.
Go home, that will go back to the initial start node. And we're able as well to expand and change the size of any of these main panes. We can even hide them if we want. We zoom in, we can drag, we zoom out, pan anywhere we want. We also can use these very modular controls.
This side panel with JSON, this is probably useful only for the author. I don't imagine any user actually using this JSON editor to do stuff.
And refreshes our data, everything that we get here. We finally can also delete the session as if we want, or create a new session. We'll just put the default value here.
So this is like IPython, but with a graph.
As you see, the session is defined by an execution path, which are these relationships that go from one node to another. This dictates how the program will be executed. I want to go over one more thing I didn't show. If we go to File,
And I think if you have those connections like this, you can create some pretty fun loops. And I don't know if you can do control flow here, but it feels to me like you could. Well, this is a really nice environment, I have to say.
Manage add-ons, we can see now the add-on manager. The add-on manager shows all the IGC components that you can add and are.
Okay, so we can describe classes. So sort of like inheritance diagram.
Currently inside of the application. If we want to disable a specific node, we can just select it, hit disable, and it shows disabled. Once we enable it for now, we can see all the separate packages. So in this sense, we have 3 default packages, each kind of corresponding with their separate thing. But the intention is that the user will be able to add any package that they might want from the community per se, or maybe specifically for a specific language. For instance, maybe they don't want all these object-oriented like nodes, such as class or abstract class or method. Maybe they want something more specific to another language. The user would instead just import the package specifically designed for this language. The main focus throughout the development of IGC was focusing on 4 case studies to see if we could accomplish all of the main components we felt were part of these case studies. First, was seeing a computational notebook. Next, projectional view, inspired by Pesca J. Next, there was the exploratory programming type of view. And finally, there was a compositional or architectural view. Let's look at all of these in the UI. The initial case study we'll do is try to resemble most of the features that we see in an incremental programming environment, such as a Jupyter notebook. If we click one of these cells, you can see that we can edit the cell exactly as the same as a cell that we would have in a Jupyter notebook environment. We can also create this documentation node that also accepts Markdown similarly. where also we see executing each cell one by one to get potentially an output or data corresponding with the execution of the cell. If we branch all of these together, we get a narrative of what we're trying to accomplish from the project itself. If we move on to the next case study, which ties in a lot with the first case study, is we want to have a projectional view of all of these nodes together. So from this execution that we see from the session, we're going to select projection, execution. And now we see a very similar view as we would as a Jupyter notebook on the right side. If we want to potentially just see the documentation attached, we can just deselect the code, and we see all the documentation in this project. On the other side, if we just want to see the code, we can deselect the documentation, and we see all of this. Let's try to get a little bit into a more complex example for the case study for projections. So if we go to another more complex file, let's do test or test graph, we see there's a lot of things happening here. For instance, we can maybe try to have a projection on the class that occurs with an animal. So if we go back to the projection view, we have different types of projections. Let's try to see the class projection. We're now seeing all the associated code and documentation for the animal class. Don't have any documentation as we see, so we're only seeing the code. Potentially we want to see actual dependencies. So if we look at the dependency, and we select a specific type of dependency, for example animal, we can see everything that's changed to the animal class that views it as a dependency. Let's move on to our next case study. This specifically falls under the exploratory programming view. So let's put, for example, we have this Jupyter notebook like chain of code fragments where we're trying to calculate time spent on many different tasks. We have this chain. You can see at the very end of the chain, so a projectional view, we see that we have some output resulting from this chain. And if we look, the output is suggestions save 3.3 hours by reducing time spent on write report, all stemming from this input data. Let's say, for example, we want to change this input data and see the effects to potentially this. How do we do that? Well, we have this first session. Let's go to the exploratory programming view. If you deselect all the nodes and go to the exploratory programming view, we see all the sessions that are available in the current graph. If we want to change, or we want input data 2 instead of input data 1, let's right click here. And we're going to do replace a node. We can select any of these options, but in our use case, replace a node is most valuable. We replace node, and you see all of these nodes now are highlighted green. Let's select the input data 2. And we'll name this, instead of session 1, session 2. As we see, the graph is now updated, and we're now in session 2 with the new input data. If we look, we see now that the output of the suggestions saves here by prepare presentation by 10%, which is different. We also can look at the projectional view from this execution, where the input data is now changed. If we want to go into a little bit more of a complex example, let's go to this file, where there's many different sessions. The exploratory programming view gives us a better explanation of all the different sessions that have been executed on the current graph. So we can switch, and we see that the red path stemming from the root of the tree gets updated, as well as the execution path on the graph itself. Let's go into our last case study. This is where we have subgraph nodes all contained in a node itself. For example, we want to make potentially some abstract diagrams of graphs themselves. In this graph, we try to resemble the relationships between the model view controller type architecture. If we see on the left side, we have all of these files that relate specifically to a typical, potentially component or system in our project. If we look at the projection view, we can see all of this. So you see there's the view, or display, basically, let's just do a test input of 5 for now. On the model side of things, we can see as well that this is just representing specific data that's stored for now. Finally, for the controller, we have this, where we then can display the actual data from the model to the view. Each of these graphs you see on the left side is encompassed by one of these graph nodes. In the future, we'll have more features to actually show relationships between all of these, but you can think about scenarios where complexity might get very, very big with large projects. And specific components or systems can all be encompassed within specific graph nodes. When you select the graph node, the user has to specify the file specifically that they're referencing to import. Next, they have to specify the session that lives inside of this map. So if we see here, we have only this session, and this session has this execution path that is here. So when we go back, we have the session, and we can see also the corresponding data that's attributed to this session from this file. You can use a relative path, you can use absolute paths, you can also use the file directly. We also can add documentation. But now we can use these graphs all encompassed in this one node in this new graph object.
Master's thesis. So this is somebody's master's thesis. This is a killer master thesis.
There's many different situations potentially where you might want to have
This is a good for a PhD.
a subgraph all contained in a node. It's also reduces
Reductor
complexity
says,
by having
What's
everything
the recent future of code
separated
dev
into
in a
individual.
TLDR?
Go over some final thoughts. IGC is trying to get the benefits of multiple environments all into one environment.
So there are two cool new projects. The first, they are both in a kind of semi-finished states. The first that we took a look at is probably the best functional coding, the best visual interface to functional coding that I've seen. Okay, this is called Drostes layer. You can check this out, it's very quick. It allows you to do a sort of programming, like you can create a simple step, right? You can perform one step here, and then you can use some funny symbols to execute it recursively. So I took first element on the list, I added it to a new list, and by applying this recursively, I can reverse the whole list. This applies this chain of commands like recursively until it finds an error, because it cannot execute anymore. I can tell it to, hey, when you found an error, just return the result up. And this allows me to kind of flatten the list. I can hide all of this complexity just so I can see the first recursion level. So it allows me to kind of program in a very nice, very visual way. It's very constrained right now, because this is an early experiment, but it's a very well implemented one and a very well thought. It has just the right tools to do everything that you might need to do. I mean, not everything, but almost everything. Oops. I don't want to do that.
Functional program hasn't been the future for a long while, though. It's been around for a long while without enough traction.
Yeah, this is not a good indicator of this being the right approach. It's the same as with neural networks, right? We had neural networks since the 70s, right? It's about the implementation. The implementation has to be done well, and this is a good implementation. So Drostes layer is one idea. By the way, I agree with that functional programming is probably not the right way to kind of compute in general, but for a different reason. In addition to this, I recommend checking this out. It's nice, it's very short. We also have this TL-draw computer, which is this is a way to chain LLM and image generator, image generation, text synthesis, like all of the trendy neural applications of neural networks into something that it's very easy to create sequences of commands here. You can write a short commercial about Nike's AI-powered smart gloves, right? It writes it for you. It does TTS, so it generates a text that reads it. it does image generation, so it can show you the amazing hands that only AI can generate. It can generate variants of this stuff. My favorite one was, so Email Factory. This is an example that writes, it's not an email factory. There are probably some messed up kind of plumbing here. But Email Factory, this is a really nice application that can give you an email about any topic with a given degree of professionalism. This is almost practical. And this is, I guess, data flow, or something close to data flow. It's not strictly data flow, because data flow is a very mathematically constrained way to program, but it is almost like data flow, and a node can look at the nodes around it. Like, this is the only exception from the classical data flow. This is me. This is my computer asking for update. So we took a look at those two.
Element man, should move you.
Sorry, my TTS is having a stroke. I can see the chat though. So those were the two cool, recent, like I would say bigger releases. We also took a look at this smaller one, which is about just exploiting graphs to represent code. Once you represent code as a graph, you can do like fun stuff with this.
It's already made.
Like generate just slices, like show me a documentation, show me. I like this. There was one example here where he shown the same set of nodes, but there were multiple different paths through this sequence of actions. That was very nice. I think this is something we could use in Automat. And the idea with implicit connections, so that when you select a node and when you execute it, it creates an arrow from the past node to the next one. That was also a nice idea.
And we see that the graph all container there.
Yeah, so somebody has created like an incredibly overkill master's thesis.
Control flow graphs are good. Personally, I feel the textural representation easier.
Yeah. I see that a lot of those graphs are very messy, especially the bigger ones. You have just a big spaghetti of arrows. In his design, he's using colors very consistently, and they actually make the picture clearer. So the blue always represents the sequence of execution. The yellow always represents dependencies. And I actually don't know what the red and purple represents. The purple, I guess, is documentation or comments. Colors help with spaghetti. The colors make spaghetti less spaghetti. This is a nice thing. Nice observation. But I would stay away from arrows if I can. So the plan for Automat to handle logic is actually... I can change the volumes. The plan for Automat is actually not to use arrows to handle... Whenever you have to do decisions in Automat, you cannot do any decisions right now, right? You can only do a simple sequence of actions. and Automat is broken, by the way. So even sequence of actions is terribly glitchy right now. But the plan is that we will actually use assembly to do decision logic. I should pin this. Yeah, this is one of my favorites. I think we will rather do assembly than Python first. I think I'm leaning more and more towards this thing. Well, it depends how you implement this.
Assembly is just asking for issues.
So assembly can be executed in a fairly sandboxed way. I mean, I'm not going to sandbox it, but as long as you don't use any memory accesses, as long as you operate only on registers, you can implement pretty decent, pretty complex logic, I think, in a fairly simple way. And it could be even better if you attach some reasonable comments to registers.
Sandboxed, you'll want a defined API.
Yeah, I was also thinking about that. Like the PCs that I'm using currently, they are all x86, but Macs, for instance, Macs are often ARMs now. Anyway, the plan for Automat is that we will have an object similar to a timeline. It will be a more complex object with like more buttons. It will have a table and a drag and drop interface that will allow you to just create sequences of assembly instructions, and you will see immediately how it executes. We could run it in a dedicated thread without any locking, without any mutexes. We would just like read the thread's memory in a totally unsynchronized way and just display it. And I think it will be so cool to have an assembly running at full native speed that you can visually edit in real time. I think it will be really real fun. This will be like allowing the user to access the full kind of power of their CPU. I don't think anybody has done anything similar, so it will be interesting to do that.
x86 doesn't define the API, it's more the OS. The text-to-switch makes me sound aggressive, lol. Native assembly doesn't mean fast. Handwritten assembly is often not very fast.
Well, I mean fast in a sense that you will get like 4 billion instructions per second, something like that. Because like I said, we are not going to use any locking, it will just execute, right? It keeps crashing. Right, when you put any operations, it will just immediately kind of get mapped to memory, changed to, like, we will add the execute permission and just jump there.
Writing C, Rust, etc. would still be as productive.
I'm not sure. So for programmers, maybe, but not for like regular users. And I actually think assembly is easier than C or Python or any programming language, really. Because it's so primitive. You can only, add registers, shift, do logical operations. It's so constrained. And also access memory. It's so constrained that I think for a newbie, assembly should be easier to grasp than any programming language. And also it will give them more power, I think.
Assembly is far from easier. Once you try to do anything slightly complex is hard.
Yeah. True, true. Any sort of complexity usually produces errors, issues. I wonder why shadows are so inconsistent. I messed up the rendering layer completely, but we introduced some nice features. It may be a little bit buggy, but I will fix the performance issues, and soon we will do some cool things. Once I fix all of the rendering issues. Oh yeah, segmentation fault. Address 28, this keeps happening. I wonder where. Just for fun, let me run a debugger. I just want it to crash. Not super relevant. Okay, so my plan is for the remaining week of this year, I will fix the rendering layer. That's one. And next year we are doing assembly. I have to make a decision. I guess assemblies make sense. I know Automat feels very incomplete. Like the mouse control is very rudimentary. We can only press buttons. We cannot control gamepad yet. We cannot edit the timeline once we record it. But I think assembly is going to be very critical to how control flow in Automat is going to work. So I would like to implement that.
Assembly is good to learn, but I wouldn't try for production code for it.
I'm not sure. I would. So my gut feeling is actually that assembly is actually quite reliable. Once you get it done, once you get it working, it will never break, pretty much.
I've spent about 20 years working with assembly off and on. Shit is a nightmare.
It really depends on how complex are the programs that you write. And whether you are using any esoteric CPU features. Like some of the flags, for instance. Sometimes you just have no idea that the CPU has set some flag and it influences some opcode, like much further down. Forgetting to save some registers or restore them. This kind of stuff can be annoying, but this only becomes annoying when you work with large programs and only because, or when you interface with different systems. And only because the environments for working with assembly are they don't give you any feedback. You just write text and you see how it runs. You cannot really see how it's executing.
Assembly becomes outdated quickly. Write for some old x86 FPU, and suddenly SIMD comes.
That doesn't make it obsolete though, right? I know you're playing devil's advocate,
And you'll never manage to be a compiler's register allocatoen, instruction scheduling, etc.
for this I'm not so sure. So usually when you have a kind of critical section of code that you want to optimize, and parallelism is not within scope, I think then people still go back to assembly. This is still the way to implement critical code sections. Or like, the kernels. The kernels for key operations are still implemented in assembly mostly.
You don't go to assembly. You might very rarely use intrinsics.
True. With intrinsics, maybe. The thing is, intrinsics, you kind of have to use those memory layouts. When I used to work at Google and we were writing for Android, we still used assembly to do like important stuff. We didn't use intrinsics. I wonder why. Because sometimes you don't want the compiler to kind of insert stuff between your instructions. We had situations like that where we actually wanted the block of assembly to execute. I mean, a compiler wouldn't do that, right?
Google used assembly? What team?
I used to work on bot detection on anti-abuse. There are some ways to detect emulators or scripts that rely on assembly. They exploit kind of hardware, some nuances of how hardware executes assembly instructions. Those were a little bit architecture specific, but not always. Some of them were actually cross-architecture.
Beakree says,
Good afternoon.
Oh, hello. But I think the assembly that I would like to use here is very different from the assembly that is frustrating because it's finicky or because it's using, esoteric CPU features. Look at that.
Reductor says,
Emulation detection. I feel you would take advantage of writing assembly, but not be any real logic. Similar to any obfuscation, you would use assembly, but the business logic would never be assembly.
I think the reason people don't like assembly is because the development experience is very bad. Because fundamentally it's not complex. In fact, there are far fewer moving pieces in assembly because you only have CPU registers. Okay, maybe this is one way to put it. If you don't care about memory of the computer, only about registers, this is a set of assembly that's actually very well constrained, and I think you can create a very decent development environment for working with assembly without accessing memory of the computer. Just on registers, only registers. Once you access computer memory, you have to do this action at a distance, which makes it more complicated. And once you access the black arts section of the Intel ABI manual, then it becomes tricky. But the regular arithmetic, bit operations, this kind of stuff, I think this is a much better alternative than spaghetti of arrows that dataflow programming uses. Or not dataflow. Or maybe dataflow. Or flowcharts, yeah. So the way we would use that would be, how would we use that? Okay, this I can delete.
Even regular things, when you're doing handcrafted assembly, you'll write things to be readable, which isn't always the best for instruction scheduling, which compiled code with end up.
I'm not so sure. I'm familiar with architectures which actually care about order of instructions. But I think the whole point of, superscalar CPUs is that they can work around it internally.
There is a reason why optimized code becomes harder to read than unoptimized code.
So the way I kind of see this is that the user will have some kind of repository of assembly instructions. This could be a book. I will create a book here. So this is a book, this is a spell book, kind of. And the spellbook which will contain, for example, an instruction like add or move. And maybe we'll have some way to search this spellbook. There should be some kind of search ability. And below each instruction there will be maybe some text explanation or some animation which shows how the instruction works. So there will be some crazy symbols like that. I mean the spellbook aesthetics because of the Droste that I just recently took a look at. It's a really nice, idea. So there needs to be a way to search through this spellbook. Let me add a search text box. Or maybe an index, yeah, there could be something like an index here.
When they want to write molreg, will it do shift left instead?
No. We could add a separate optimizer that could take the assembly and try to replace it with equivalent, more optimized alternatives, but I don't think it will be done by default. There could possibly be like an optimizer object that would take your assembly program and output a better, more optimized one. So when you browse through this spellbook, you will find different instructions, and it would be nice to kind of pull them out. Maybe you will be able to tear pages out of this spellbook and put them wherever you want. Then there will be this option of actually creating a program.
With the registers, will you have a volatile and non-volatile set? Or attempt to do liveliness detection and push the ABI non-volatile buttons?
What do you mean volatile? You mean the one that are clobbered, where you when you call a fan? Let me see volatile. I don't know the terminology.
Yeah.
So I think so. There will be some editor. The user will write the program, and we will map the program in memory, and before it executes, we will kind of clean the registers and prepare them for execution. We will execute the program. I don't know if we can execute the program for a limited number of steps.
Push up Popa?
Something like that. I would like to give the user a full thread so that if they want to write an infinite loop, it will be just an infinite loop. It will just work. But they will be able to write a program, right, using registers. So the only way that a core can communicate with other cores is through memory. So actually the program has to write its results somewhere for them to be inspected from another thread. Oh well, anyway. So we'll clean the registers, we will kind of map their code, map in memory, make it as executable, jump there, execute it as much as we can, maybe forever, I don't know. And then when it finishes execution, we will make a decision of what to do next based on the contents of the registers.
Communicating through memory becomes its own complexity, especially if looking at portability.
Yeah, so within a single ABI, like something like x86 or within ARM, I don't think Automat programs from x86 will be executed on ARM or vice versa, not natively. Emulation maybe. Anyway, so the user will be able to drag and drop instructions on this canvas, and this canvas will have literally registers, all of them. I don't know how many x86 has. $16, so not that much, not that many. So we could have 16 columns, Excel style, right? And we could show the contents of the registers. Then when you put an instruction, for example this add, right? An instruction can be parameterized. So an instruction, once you drop it, you will be able to configure its settings by toggling switches or selecting stuff like that. Maybe I should erase that. So there will be our registers. And there will be some visualization of what the instruction will do. And in the row below, you will have, like the updated, like the highlighted register, which kind of contains the updated state. And you will be able to chain instructions like that. It will be very verbose, but I think it will be also very readable, even for non-programmers, for non-experts. There will be plain English explanations. There will be very clear kind of display of what's happening. And when you actually click execute,
Data flow and control flow graph. If you're going data flow graph, you might as well go with a near SSA form with no register name.
Yeah, I was thinking about that, but because LLVM makes this very convenient. In LLVM, creating SSA is LLVM IR is a nice intermediate kind of architecture. Because it has kind of infinite number of registers, however many you want. But LLVM IR also feels so detached. I want to kind of establish a sort of intimacy between, a user and the CPU. I think the less abstraction, the less indirection layers, the better we are.
LVM here, you don't have any direction connection with the actual machine registers. Detected is a good thing. Those abstraction layers are good thing. Optimization passes are dependent on those.
Yeah, but there is some magic happening there, and I want to remove this magic. So the point is to have somebody who is like 10 or 12 years old, who's playing games, to be able to program assembly, and not some fake assembly, not some baby abstraction to make things easier. I want them to feel the real thing, to have full access to the actual instructions executed on the CPU. We can have facilities, for example, to do the optimization, or a different version which would actually use LLVM opcodes instead of actual x86 opcodes. But I think this base layer is the most important one, to actually not hide it from the user. I also was thinking, so I don't know how to visualize registers, because registers can hold arbitrary memory. They can hold floating points. They can, right? Usually integers, but you can copy a floating point into one of those. You can have stuff like the registers are hierarchical themselves.
What's the purpose? Sorry if it seems I'm being critical. I spent a lot of time doing low-level optimizations.
So the point is to give somebody a building block that they can use to build more complex machines. And this building block should be as easy to use and as powerful as possible. So in an environment like Automat, where you are building machines out of smaller kind of components, the more and the more capable building blocks you get, your power increases exponentially. So the point is to give the user more and more and better tools.
People build complex machines without assembly.
Yeah, absolutely. The point is to find a good tools to build machines out of. You can build machines out of high-level abstractions like TL-Draw computer, right? You can build a machine out of LLMs and image generators. And it will work. It will excel in some cases. But I think assembly is a good tool to have if you want to use your CPU. If you want to use your CPU to the greatest degree, manually written assembly is the way to go.
If you have just standard building blocks, then you can do typical data flow analysis and build better assembly.
So I'm not sure if this is easier or harder, honestly, for the user. I think this approach with a table, could be a better alternative to flowcharts or to math, right? When you want to compute something, compute a math equation, you can write the equation and I can generate assembly for you, right? That's one option. But you can also use this raw CPU instructions to compute whatever you want. I think this gives you more also visibility into what will actually happen.
I have seen a lot of people try to write assembly to be more performant over time, and nearly always it wasn't better than just some well-crafted CC.
I don't believe that. This is not my experience. Just honestly, based on what I myself have seen.
Don't believe it all you want. This is just decades of dev.
So for instance, C++ will, for example, and C, they will insist on committing stuff to memory. Yeah, that's one thing. And in assembly, you actually have to be very explicit about that. And copying stuff to memory is the slow part. Oh well, I will have to brush off my assembly, because I haven't used it in a couple of years.
You'll typically get stuff in memory when spilling is needed, being a reference because of an ABI or register exhaustion or not. But again, look at knowing what you do can avoid this.
But the thing is, to write good C++ that will actually compete with assembly, you have to know the assembly. You need to know, for example, that you have to use the restrict keyword, right?
Writing assembly doesn't make a good assembly.
I mean, yeah, of course. The thing is, I think it's a very simple abstraction. So it has three different things going for it. It's very simple to do math. It's very easy to do control flow with assembly. But by simple, I mean somebody who has never learned programming can look at a visualization of how assembly works and some simple explanations, a gamification of assembly, and it will click for them. This is not the case for languages.
Math isn't always that easy. Look at any divide or multiple, the compiler will beat you.
Yeah, I mean, there are tricks to divide using multiplications, true, but still, it's missing the point. It's easier. It gives you this closeness to the CPU, and if you know how to convert a divide into a multiplication, sure. We can have optimizer to optimize the assembly or a different, environment. But I think the one which is closest to the machine is the most important. I think it will be very hard to write slow programs in Automat if we rely on assembly for logic, for math, and for control flow.
Closeness to the CPU, but then you suddenly misalign a branch. Add a bad data dependency. You'll slow things down unexpectedly.
I think with the size of the programs that we will write here, they will fit perfectly fine in any CPU's cache. So I don't think branch prediction or speculative code execution is going to factor in any of this. So just FYI, I expect programs, most of the programs will be around 10 instructions long or shorter.
Fitting in a cache isn't everything. Branch prediction still plays a big part, same with the unit cache.
Yeah, and even instruction cache, right? How long is instruction cache line? I guess it will fit the whole program.
Cache, you will pay cash. All complexities that people don't think of.
I have to specify specific. Okay, there is a way to ask what's the length of the instruction cache line on the CPU. But yeah, if it's 64 bytes, then a program will fit in a single instruction cache line. A typical one.
The iCache line size is one part, but then look at UOP cache details, it gets more complex.
What is UOP cache? This is about how CPUs translate the x86 to the whatever they actually execute. I have no idea how any of this stuff works. I mean, I know the vague details, but I never really looked into the details. Okay, I am not discounting having something like LLVM as well. And even if we implement this for x86, then we will also have to implement something like this for ARM. Yeah. We will have to think real hard about how to give user access to assembly. Because this will be the main way to do control flow.
Optimizers have built-in information about many URCs for optimizing for specific processors, which allow optimizers to do these things better. So for x86 2 CPUs, the ideal instructions might be different instructions and different ordering.
I think this is about really tiny things. So I'm running Gen 2 with March native, right? Right. So this is how I compile my stuff, my kernel and everything. This is all March native, all optimizations. I've only disabled fastmath because that was causing issues. This brings some performance improvement, but it's really not that much. It's a couple of percent. I think it was like what, 10%?
March native is the big one there.
Yeah. Because you would otherwise have to specify exactly what extensions do I have. And you also said that specific processors, that a compiler knows about specific processors. I didn't know about that bit. I don't know. Is there a way to inform a compiler about specific processor? I thought this is only about architecture and maybe, yeah, the version. Or actually no, you specify it like that. Huh. Interesting. I had no idea about those new architectures actually.
Yep, the UArch allows instruction sets and also changes other things like timings.
So in principle, we could express computation as data flow graph, but then to actually execute it fast, we would have to compile this graph. And this compilation of the graph, I mean, would we do this behind the user's back or like automatically, or would the user have to do this explicitly? Like, is the compilation explicit or implicit? If it's explicit, so the user has to actually compile it, then it's adding complexity that I think new users will not take advantage of. And they should actually like get the most out of this. And doing this implicitly doesn't feel right. Like taking a graph and just quietly compiling it behind the user's back. Feels weird.
Jitted.
Yeah, exactly. Yeah, I would like to create just a very good environment for writing assembly. I think this will be still a good thing to have, regardless of how many people will use it. And I would like this environment to be the basis of... I would like this to replace the typical spaghetti that node and wire environment use. I think if we do it well, it will work. Similar to human resources machine. Sorry.
I think it's worth doing regardless, even if not successful.
So there was this game which used the idea of assembly, although with a fake, like imaginary. It's a toy assembly. It's like for the purpose of the game.
The best way to learn is pushing the boundaries.
Yeah. We'll see. I still don't know how to do the visualization. I think it will be very good to visualize the data. So there is some benefit to visualizing the data and code at the same place. It's like Excel. In Excel you mostly see the data, the instructions, the formulas are kind of hidden from you. I think we could create a mix. So a computer is not a two-dimensional grid, it's like sequential. I mean, it's not even sequential, it's just a list of registers. They are not actually ordered in any way.
If you're visualizing data, it would be interesting to see if you can also overlay things like SSA, liveliness, dominators, etc. Dawn.
I remember dominators from LLVM lingo. I don't remember what those were. Yeah, but I think there is a way to convert x86 to sorry, x86 to LLVM IR, yeah, exactly. Yeah, we could use something like that to go back and forth.
You can build a bunch of this from x6. I've done it before building decompilers.
Like, all I care is that it should have a BSD or, I mean, it says AGPL license. They said it actually has BSD. Maybe older version has BSD. Or maybe it's dual licensed. So we could do optimizations. And we could write natively in LLVM IR. But having your feet on the ground and the ability to like see registers and have like precise control over what instruction you're adding, that would be nice. That would just be nice. Yeah, it depends how we build the UI. Maybe we don't have to show all of the registers. Or maybe we could... yeah.
Hey,
Dynamically change the number.
we're gonna float around Twitch. Was good chatting.
Yeah, same here. Actually, Christmas coming, so I'm doing shorter streams today. So I'm ending the stream as well. It was nice chatting to you.
See y'all.
Okay, I guess this is it for today. I promised I will not be doing any coding today. I will probably do some coding off stream just to fix all of the display issues. There are some bugs, new performance issues. They are all going to be easy now. I solved them, the nastiest of them all already. That was an ABI issue actually. So, yeah. I may not do a stream on Wednesday. Yeah, I think I will cancel the Wednesday stream. On Friday though, I will probably do a stream as usual. So, see you probably on Friday. Bye.